Yes.
Okay. So the next talk is from Professor Nakato that we would like to thank for being here with us in this event. So her presentation is titled A Graph-Theoretic Criterion for Absolute Irreducibility of Integer-Valued Polynomials. So you have 30 minutes. The floor is yours. Hello.
Thank you. Nice to see you.
Nice to see you too.
Good afternoon, everyone. Thank you all for joining. And I'd like to thank the organizers for bringing us together and for the invitation. So like the title says, I'd like to share with you a graph-theoretic criterion for absolute irreducibility for integer-valued polynomials. And this is joint work with Professor Sophie Frisch. Professor Shems is saying something. I see the hand is up. No. All right, thank you. So I'll start with a few remarks on int d. Good enough, we've already seen this ring of integer-valued polynomials. Then I'll give a recap of factorization terms, and then I'll go straight away to absolute irreducibility. Okay. So int d, we have a domain d with quotient field k, the ring of integer-valued polynomials on d, which you've already seen actually. We denote it by int d. It consists of polynomials with coefficients from k that map d to d. So these are special elements of kx, such that when you input an element of d, the output is in d. So it's a subring of kx. So it's a subring of kx. Which elements of kx are in this int d? So it's what we should look at next. That if I have a polynomial with coefficients from k, I can always write it as a quotient g over b with g in dx and b non-zero. And written in such a form, f is an int d, if and only if b divides the images ga for all a and d. So this follows from the definition that I want the images to be in d, so I need the b to divide the images of that numerator for all the elements of d. Some examples, dx is trivial in int d, but you can have those outside dx. For example, this polynomial is in int c. When I pick an even integer, this is even. When I pick an odd integer, this is even. So each integer I pick, the image of the numerator is even, now in particular divisible by 2. So I get something in z. Okay, so actually this polynomial belongs to a special type of polynomials, which we call Fermat's polynomials. That for each p, each prime number p, x to the power p minus x over p is an int c. They are Fermat's polynomials because it follows from Fermat's little theorem that actually for all integers a to the power p minus a is divisible by p. So there are other number theory results that can give us elements of int c. For example, a product of n consecutive integers is divisible by n factorial. So that can also give us elements of int z. Okay. So this structure of integer-valued polynomials, int d, as we've seen in Professor Francesca's examples, and in the talk of Professor Francesca, it's known to give friendly examples. It's a friendly ring, just a subring of kx, and we've seen several examples in Professor Francesca's talk. So int c is a friendly example of a non-Noetherian ring. We've seen that it's proofer and non-Noetherian at the same time. But for this talk, since we are in factorizations, we are interested in the fact that int d in general is not a unique factorization domain. For example, So by not a unique factorization domain, it has the failure of uniqueness of factorizations. So just like we've had in the previous talk, in the earlier attempts to prove Fermat's last theorem, so they tried to use the unique factorizations in rings of integers of number fields, but it happened that this is no longer true in an arbitrary ring of integers in number fields. And then it led to other developments. It led to ideals, actually, in a way to bypass the non-uniqueness of factorizations of elements. Okay, so this polynomial is in int C, and it has two factorizations. This is covering the evens. This is also covering the evens. So I can always do away with one of them. So these are two factorizations of this particular element in int C. Okay, so actually it's known that int D has quite wild factorization behavior. In particular, we proved with Professor Frisch and Dr. Riesner that given any finite multiset of integers greater than 1, say 2, 3, 3, 6, there exists a polynomial h in int D such that h factors into 2 irreducibles, it factors into 3 irreducibles, other 3 irreducibles, and 6 irreducibles. So this is true for any arbitrarily finite multiset of integers, as long as they are greater than 1. One can always construct a polynomial h in int D with this behavior, but for particular domains D, not any domain. Okay, so I've been talking about irreducibles, factorizations, but I haven't defined them formally. So let's look at that. So our R is a commutative ring with identity. A non-zero non-unit R is said to be irreducible in R if whenever R is a product AB, then either A or B is a unit. So by a unit, I mean the invertible elements. So for example, the prime elements are irreducible. So you can't write R as you can't split it into two non-units. So all prime elements are irreducible. By a factorization is also what we know. A factorization is an expression of R as a product of irreducibles. Another definition we need are the associates. So we say that two elements S and R and S of R are associated in R if there exists a unit U in R such that R is US. So R and S differ by a unit. And we denote this by R is associated to S. So for example, 3 and negative 3 are associated to each other in Z because the units in Z are 1 and negative 1. So these are associated. Okay. Now for factorization theory, or in this theory of factorizations, we can have two factorizations and for us, we consider them to be the same. And in other cases, they are different, as we're going to see. So in particular, two factorizations of the same element, these two factorizations, we call them essentially the same if they contain the same number of irreducibles. And after a suitable reindexing, AJ is associated to BJ. Otherwise, we call them essentially different. Okay. So a quick example. This one can say in this ring of integers of Q with root minus 5 adjoined, we have 14, one can say it's 2 times 7, but it's also negative 2 times negative 7. But for us, these are essentially the same because 2 and negative 2 and 7 and negative 7 are associated. Whereas the second factorization, so we see that these are clearly essentially different. Okay. So we go to absolute irreducibility. R is a commutative ring with identity. So we call an irreducible element absolutely irreducible if for all natural numbers n, every factorization of c to the power n is essentially the same as n copies of c. So that's an absolutely irreducible element. So I have an irreducible, I raise it to a certain power, I expect it to give me exactly n copies. So that's the expected behavior. However, this is not always true. For example, so there are some examples. I gave some examples of the absolutely irreducibles. The prime elements are always absolutely irreducibles. For them, they always behave well. But the surprising irreducibles are the non-absolutely irreducible. That if C is irreducible, but there exists a natural number n greater than 1, such that C to the power n has other factorizations essentially different from the expected one, then C is called non-absolutely irreducible. So this is the expected behavior. This is the surprising behavior. I have my irreducible. I raise it to a certain power. I expect just those copies. And again, it gives me another factorization. So these are surprising. They are surprising, but not bad, because we use them in other areas. For example, the non-absolutely irreducibles are used to study patterns of factorizations. Okay, so let's look at some examples of these. Okay. In this particular ring of integers of q with root minus 14 adjoined, 3 is irreducible. But when I raise 3 to the power 4, it gives me 4 copies of 3. But it also gives me another factorization. In this case, actually, it shrinks to 2 factors instead of the expected 4 factors. So in this case, we say that 3 is non-absolutely irreducible in this particular ring of integers. So more generally, it is known that whenever I have such a ring of integers of any arbitrary number field, and that ring has non-unique factorizations, I will always find such elements like 3 with this behavior. In particular, an arbitrary ring of integers, OK, of a number field K, is a non-unique factorization domain if and only if it contains non-absolutely irreducibles. So this is a result by Professors Chapman and Krause, that once OK is a non-unique factorization domain, I'm certain there are such elements with this behavior. So likewise, in our structure of integer-valued polynomials, so it's one of those examples where we can find such behavior. In particular, there is this example. It's an INSEE. So we have f squared giving us the expected factorization, but it also has this other factorization. So these are different elements. And what is happening actually is that x and x minus 4 are playing the same role in this polynomial. They are covering the even numbers. And they are both needed because of the square in the denominator. Whereas for the odds, this x squared plus 3 covers the odds on its own. So when I square, I can always do away with the other polynomial, which plays the same role. And we call this behavior interchangeability. At least 2 polynomials playing the same role. Once I raise to a certain power, I can do away with the other. So they are general constructions, actually, of non-absolutely irreducibles. In this particular paper, I'll give the reference. So this is one type, but there are other types. I'll give the reference at the end. Okay, now we are ready for the graph-theoretic criterion for absolute irreducibility. We start with a few definitions, which you already know, actually. that our D is a principal ideal domain, which we denote by PID with quotient field K. Actually, from now on, our domains are principal ideal domains. So a polynomial G in DX is called primitive if the GCD of those coefficients is 1. That is what we know already. Another definition, we need an expression that every non-zero f in Kx can be expressed as such a quotient. Remember, at the beginning, we had G over B. So what is happening here is we are writing G explicitly, factorizing it. So A, B are non-zero elements of G. Their GCD is 1, I is finite, and each of these GIs is primitive and irreducible in DX. And we'll call such an expression the standard form of F. I'll be referring to it later on. Okay. Another definition we need is the fixed divisor. So G is still a principal ideal domain. So G is in DX, then the fixed divisor of G, which we denote by GG, is the ideal generated by the GCD of the images. The fixed divisor is the ideal generated by the GCD of the images. But because D is a fixed divisor, we normally abuse notation and just write the generator for the ideal. Okay. Another definition we need is image primitive. That a polynomial in int D written in standard form is called image primitive if A is 1 and B is the fixed divisor of that numerator. So in that case, we call it image primitive. So what is happening, if we remember from the definition of integer valued, for such a polynomial to be in int D, we require that B divides the images of the numerator. So what is happening is that images here are now represented by the fixed divisor. So for such a polynomial to be in int D, we require that B divides the fixed divisor of that numerator. And now for image primitive, we need that it not only divides the fixed divisor of the numerator, but it's exactly the fixed divisor of the numerator. So irreducible polynomials are actually always image primitive. So later on, from now on, our polynomials are going to be image primitive, those which are in int D, numerator over its fixed divisor. Another definition is what we already know. D is still a principal ideal domain. P a prime element. The periodic variation of A in D, which I will continue denoting as usual. Vp of A is the maximum n in Z such that P to the power n divides A. And it follows that the periodic variation of 0 is infinity. And with all those definitions, we are ready for the criterion. D is a principal ideal domain. I is a non-empty finite set. And for I in I, GI is in DX, primitive and irreducible. And GX is the product of the GIs. And P is a prime element. So that's our setting. So we say that GI is essential for P if P divides the fixed divisor of that product, and there exists a W in D such that the periodic valuation of GI at W, that image, is positive, and it is 0 for the other GJs. So I only get something positive for that particular W at GI. All the others GJs, I get 0. And in that case, we call W a witness for GI being essential for P. Okay. Similarly, we say that GI is quintessential for P if P divides the fixed divisor of G, that product, and there exists a W in D such that the periodic valuation of GI at W, that image at W, is exactly the periodic variation of the fixed divisor, and it is 0 elsewhere. So for essential, we require that for that particular W, we get a positive periodic valuation and zeros for the other GGs. For quintessential, we need it not only to be greater than 0, but exactly the periodic variation of the fixed divisor. So that's the quintessential. And it should be 0 for the others. And likewise, we say that such a W is a witness for GI being quintessential for P. So actually, our criterion is based on these two definitions. So may you stay at them for a few seconds. Let's sum it up. Okay, so we look at some examples since everything is based on these two actually. So we have some polynomials. G1 is x squared plus 9, G2 is x minus 4, and G3 is x minus 5. And now our G will be the product of these GIs. So we need to get a fixed divisor of this. So the fixed divisor of G in this case, which we denote by DG, is the GCD. It's the GCD of the images G0 up to G4. So one would wonder, in the beginning, we said the fixed divisor should be the GCD for all elements of Z in this case, since we are in Z. But in Z is special, that I don't have to check for the GCD of all the images for each element of Z. It's known that I only check from 0 up to the degree of that polynomial. So that's the beauty of int Z or ZX in particular. So in this case, the degree is 4. So I only check for the GCD of the images G0 up to G4. Okay, and this is actually a result by Professors Kahen and Shabeat. So I checked already the GCD and it's 6. Okay, then I ask myself, we have two prime divisors in this case, 2 and 3. Which of these are essential for 2? Those which are essential for 3, quintessential for 2, quintessential for 3. That's what you're looking at. So essential for 2, we see when we go back to our polynomials here. When I get an odd number, I plug it here. I get a multiple of 2. In other words, a positive two-word valuation. Likewise, for G3, when I get an odd number, I get a multiple of 2 or a positive two-word valuation, meaning that G1 and G3 are not essential for 2. So if I have this, I don't need the other one. If I have this, if I have G3, I don't need G1. So they are not essential. Whereas for G2, if I pick any even number, when I plug it this side, I don't get a multiple of 2. Or I get the two-word variation as 0. Whereas for G2, when I plug in this case, I chose the witness as 0. When I plug in 0, I get a positive two-word valuation. And I chose 0, but any even number in that case can be a witness. So we only have G2 being essential for 2. How about quintessential? If G1 and G3 are not essential, we cannot even talk about quintessential. We leave them out. So we look at G2. Is it quintessential? It is with witness 2. When I plug in 2, I get the two-word valuation as 1, which is the two-word valuation of 6. 6 is the fixed divisor, remember. So G2 is quintessential with witness 2. I go to 3. G1 is essential with witness 0. Because when I plug in 0 here, or actually any multiple of 3, so when I plug in 0 here, I get a multiple of 3 or a positive three-word valuation, whereas this side I get nothing. I don't get a multiple of 3. Likewise, G2, when I plug in 1 here, I get a positive three-adic valuation. In other words, I get a multiple of 3. Likewise, for G3, when I plug in 2, I'll get a multiple of 3, but all the others, I get nothing. So G1, G2, and G3 are essential for 3. How about quintessential? The three-adic valuation of 6 is 1, and when I plug 1 in G2, I get exactly the three-adic valuation as 1, meaning G2 is quintessential for 3. Likewise, for G3, when I plug in 2, I get the three-adic valuation as 1. So G3 is also quintessential for 3. Whereas for any multiple of 3 that I pick, when I plug it in here, I get the three-adic valuation at least 2, greater than the three-adic valuation of the fixed divisor. So in this case, G1 is not quintessential for 3. Okay. So that's our example. And we form graphs out of essential and quintessential. So it's what we're looking at next. That our domain is still a principal ideal domain. I is an empty finite set, and for each I in I, the GIs are primitive and irreducible. Then the essential graph of the GIs is the simple undirected graph whose set of vertices is I, and in which ij is an edge if and only if there exists a prime element P in D, such that both GI and GJ are essential for P. So our set of vertices for the graph is I, and I connect I to J if and only if I find a prime element P in D, such that GI and GJ are essential for that prime. Okay, so that's our essential graph. Quintessential is defined similarly. Still, it's the simple undirected graph whose set of vertices is I, and in which ij is an edge if and only if there exists a prime element P in D, such that both GI and GJ are quintessential for P. So for the quintessential graph, likewise, our set of vertices is I, and I can only join as an I and J, an I to J, if and only if I find a prime element P in D, such that both GI and GJ are quintessential for P. Okay, so those are our graphs. And let's look at the graphs for the previous example. So our previous example, we had these polynomials G1, G2, and G3. And we saw that for 2, only G2 was essential for the prime 2. So 2 is not helpful because I can only have an edge if I have 2 polynomials at least. Whereas 3 is helpful because G1, G2, and G3 were essential for 3. What does that mean? So I have an edge from 1 to 2, 2 to 3, and also 1 to 3. So that is our essential graph. All the edges are given to us by the prime element 3. How about quintessential? So for quintessential, likewise, 2 is not helpful because only G2 is quintessential for 2. Whereas 3 is helpful because it gives me an edge, 2 and 3. So that is our quintessential graph. G1 is not anywhere in the quintessential environment. It didn't participate at all because it wasn't quintessential for any of these 2. Okay. So our criterion is based on the connectedness of the essential graph and the connectedness of the quintessential graph. In particular, if the essential graph is connected, the resulting polynomial is irreducible. If the quintessential graph is connected, the resulting polynomial is absolutely irreducible. What do I mean by the resulting polynomial? This is the resulting polynomial. The resulting polynomial is the product of these GIs over their fixed divisor. Now, because the essential graph is connected, we already conclude that this polynomial is irreducible. Whereas for the quintessential, we can't say much at the moment because the graph is not connected. However, we shall see later on that we can deduce something from this graph. Okay. So in particular, this is what I've been saying. We proved with Professor Zafrullah that if f is an entity, non-constant and image primitive, written in standard form as that quotient, if the essential graph of the GIs is connected, then f is irreducible in entity. Likewise, we proved that f, the same actually, f is an entity, non-constant and image primitive, written in standard form as that quotient. Once the quintessential graph is connected, then f is absolutely irreducible. Connectedness of the essential graph implies irreducibility in entity. Connectedness of the quintessential graph implies absolute irreducibility in entity. So we've already looked at an example for irreducible. So we need maybe one for the absolutely irreducible. So we deduce from that actually for each prime number p, the binomial polynomial x choose p is absolutely irreducible. In this case, p is the one actually helping us because x is quintessential for that p with witness p. X minus 1 is quintessential with witness p plus 1. This is quintessential with witness 2p minus 1. So all of them are quintessential for that particular p. So we have a connected graph, a connected quintessential graph, and we deduce that x choose p is absolutely irreducible in C. Okay. One would wonder, how about the general case? So it's now known, it's a result by Dr. Reisner and Dr. Vendish, that for each n, x choose n is absolutely irreducible in C with a totally different method, actually. I'll give the reference at the end. Okay. So one thing we also need to point out is that the converse of both theorems 1 and 2 doesn't hold in general. That for this particular polynomial, it's an entity, it's absolutely irreducible, in particular also irreducible, but the graphs are not connected. That I can have my irreducible or absolutely irreducible element whose graph is not connected. So in this case, x and x are playing the same role. So that's why we can't, this is not necessary and another x is not necessary. This could be necessary, but on its own, it can't give us an edge. However, in the square-free denominators, the converse holds. So in this case, we have a square in the denominator, but once we have a square-free denominator, we have a full characterization actually. That's infinity, non-constant and image primitive with square-free denominator, written in standard form as this quotient. In this case, b is written out explicitly in terms of, as a product of its prime divisors. Then f is absolutely irreducible if and only if the quintessential graph G of the GIs is connected. In particular, once I have a square-free denominator and I find that, okay, the graph is not connected, then I already deduce that this polynomial is not absolutely irreducible. An example is actually our previous example, remember? We are in the square-free denominator environment, and the graph, the quintessential graph is not connected. We conclude that this polynomial is not absolutely irreducible. So this is not absolutely irreducible. It's reducible because it's irreducible because the essential graph is connected, but not absolutely irreducible because its quintessential graph is not connected, and we are in the square-free denominator environment. Okay. So the sketch maybe of this proof. If G is connected, we concluded from the previous theorem, theorem 2, once we have connectedness, we expect absolute irreducibility. Whereas when G is non-connected, we obtain explicitly a factorization of F cubed, essentially different from the expected one. So one thing may be we deduce from this proof of the second part is that at F cubed, I can already tell if a polynomial is absolutely irreducible or not. In other words, a corollary is if F in int D, non-constant and image primitive with square-free denominator, once F cubed has a unique factorization in int D, then F is absolutely irreducible. So I only get my polynomial as long as the denominator is square-free. I raise it to power 3. The moment I have a unique factorization, I deduce that that polynomial is absolutely irreducible. Okay. So we've proved actually more generally, but for discrete valuation domains. So with Moritz and Dr. Riesner, we have established a similar bound for arbitrary polynomials in int V. In particular, we've characterized absolute irreducibility in int V. Okay. These are some of the references. The first one is the general reference for integer valued polynomials. The second one is the general reference for non-unique factorizations. The number 3 is where we can find the absolute irreducibility in rings of integers of number fields. Number 4 is where this concept of absolute irreducibility started from. Number 5 and 6 contains the wild factorization behavior of integer valued polynomials. And then number 7 is where we can find constructions of non-absolutely irreducible elements. Whereas number 8 is the main reference for this talk. All these actually are open access. Then these are the recent ones, the latest on the same topic, to the best of my knowledge. So here we can find the absolute irreducibility of binomial polynomials. And number 12 is where we can find similar bounds as in the last theorem. And finally, these are selected publications by Professor Zafrullah on factorization theory. So I picked out these because these two actually are the backbone of factorizations in integral domains. And everyone familiar with the dx and kx? It's an amazing construction, rings between dx and kx, or the d plus m construction. Thank you.
Thank you very much. So are there any questions?
Yeah.
Yes,
Yes, sir. Well,
yeah. Can I talk?
Hakim? Abdul
Yes.
Hakim, yes.
Yes. Thank you, Professor Sarah, for your very good presentation. I want to know if there is any reference for the explanation you made with regards to the interchangeability when you are doing factorization. And secondly, on the one of your research work, I followed where they use a table method in the factorization. I don't know if there is any progress in that direction with respect to absolute irreducibility. And finally, on the work on this video, I don't know if there's any way I can have the video and listen to it over again. Thank you.
Thank you. Thank you. So for the first question, so this paper, this is where we can find the interchangeability. So in this, I studied that interchangeability and also other types of non-absolutely irreducibles. So this is the reference and it's open access. Then for the second question about absolute, because we studied factorizations, and is there any light in the line of absolute irreducibility? So like I mentioned, the non-absolutely irreducibles are essential in studying patterns of factorizations. So likewise, in this paper, in my paper, so there are preliminary constructions of patterns where one can use the non-absolutely irreducibles. So the tricky part, maybe I'll give. So the tricky part, this is scary, but it's not. Yeah, so for this one, it's an example of the patterns of factorizations. So the hindrance for using maybe non-absolutely irreducibles in factorization generally is that you can't know if it's non-absolutely irreducible, you can't know at which power it's gonna misbehave. So you lose control of the factorizations when you use non-absolutely irreducibles. And actually in all our theorems, we don't use non-absolutely irreducibles because you completely lose control. You don't know until maybe you know that at this power, these factors like that, which is not always easy to detect, then that's when you can use the non-absolutely irreducibles. But they are helpful in patterns of factorizations. For example, you can't get these patterns. These are partitions of 4. So I got a polynomial and it factors into partitions of 4. And this can only happen if you're dealing with non-absolutely irreducibles. But in factorizations generally, we try even to avoid this because you can't know at which point or at which power they are going to misbehave. Thank you. I've answered you.
Thank you very much. Are there other questions?
I have a question. Can you hear me?
Professor Badawi, yes.
Hi, Sarah.
Hello, Professor Badawi.
Yeah, I enjoy your talk, especially the part on connecting a graph to your and my question, is this published already or
Thank you, Prof. It's actually published.
What year? Here?
In 2020.
Okay. Okay. Thank you. And can I ask for a preprint or like a PDF file for this paper, number 8?
Yes, Prof. Yes, Prof.
Okay, and I will type my email in the chat if you don't mind.
Yes.
All right, Prof. Thank you.
I just typed it. Did you see it?
Yes.
Thank you very much.
You're welcome.
Thank you. Thank you, Professor Badawi. Mr. Al-Alawi, yes? Yes.
Hello. First,
Hello.
I would like to thank Professor Nakato for this beautiful presentation. So my question is there any characterization using the diameter of extension graph or quintessential extension graph? Did you get my question?
Yes, I get your question, but so unfortunately, we are not really using deep, I wouldn't say deep graph theory, but we are only borrowing some bit of graph theory to meet our needs. So for the diameter and other things, we've not dealt with them deeply. Thank you.
Okay, thank you so much.
Thank you very much, Mr. Omar. Yes, you can.
Hey, can you hear me?
Yes, we do.
First of all, we thank Professor Sarah for her excellent presentation, and it has been a pleasure for me to see her. I didn't realize, Professor Sarah, that we have met 5 years ago. The time passes very fast. So thank you very much for accepting to be a plenary speaker in our conference. And congratulations for your position in Uganda and for all the support and help you provide for the young researchers. And obviously, you are a good example to follow by the young researchers. We are looking forward to see you here in Morocco, and we are very, very proud of you. Thank you.
Thank you very much.
Professor Omar. Hope to see you, hopefully, this year. And thank you for the hospitality always whenever I come to Morocco. It's home.
You are welcome. And every time you want to visit Morocco.
Yes, hoping to see you next time here in Fez.
Yes. Yes, thank you.
Okay. Are there any questions? Other questions?
I have a question.
Yes.
Hello, Sarah. Thank you for your talk. I wanna. There is a set that you showed before. There is 3 repeated 2 times. I don't know if there is a mistake or I don't know. I see that 3 is repeated 2 times. Before in the
Do you remember which slide?
Yes.
No.
So
Yes,
it's
here.
this one.
Yes.
Yes. So 3 is repeated because actually we proved that for any finite multiset, so it can be 2 can be repeated 10 times as long as we have a finite set. 6 can be repeated 20 times. So we proved generally that not only a set, but a multiset, as long as it's finite, we can always repeat. So thank you. So there is no reason really for repeating 3. I only chose a finite multiset. So one could choose 6, 10 times, 2, 20
okay.
times. Yes.
Okay.
Thank you.
Okay. Also, I want to know the relation between essential graph and the other one. They are, for example, the first is connected. If implies that the other one is not connected, or because in the first example we yes, here we have connected, and the quanti-essential graph is not connected. Always we get this situation when the first is connected, the other is not connected.
Yes. So it stems from the definition. Thank you for the question. So it stems from the definition of when we get an edge. So in this case, we ended up with a connected graph because of the edge, because of the 3 edges. I mean, we have polynomials. I'm sorry. I'm sorry. Someone wanted to come in. Yes, so the reason we ended up with something which is not connected is because G1 was not quintessential for anything. So it stems from what we've already done up. Otherwise, if we had G1 also, maybe quintessential for 3, then yeah, we would have a connected graph. So it would look like this one. So it stems from the nature of the polynomials we have, and then when we test, and yeah, so that's how we come up with the essential and the quintessential. One connected. It can also happen actually that this is also not connected. It could happen. For example, if maybe G2 was not quintessential for 3, we would have something similar to this. Yes.
So I see that here is complete and here is not connected. For example, just only there is a problem between 1 and 3. So if, for example, these 2 vertices are not adjacent, if there is a problem here, we can situate where is the problem of irreducibility by these 2 graphs.
Thank you. I don't know if I've understood you. So really putting 1 here, I could even put it here. It's basically an isolated vertex because it's non-quintessential for anything. So it could be anywhere. Yes. It could be anywhere, actually. I could even start with it. So it's an isolated vertex. So I only put it here because I was trying to illustrate that only G2 and G3 give us an edge.
So the problem, we can see that the problem is in the vertex 1.
Sorry?
The problem of irreducibility, for example, the polynomial is not irreducible when I equal 1, for example.
Maybe we shall talk. We shall discuss later on, Raja.
Exactly.
Okay, thank you so much, Sarah.
Thank you.
Thank you very much.
We shall discuss about it more detail.
So, Salvatore. Yes?
Salvatore, hi. Hi, Sarah. Nice to see you again in the video. And I hope your year started in the best possible way. Well, I have a question of a philosophical flavor, let's say. Have you tried to generalize your criterion to the case of, let's say, a commutative cancellative monoids that embeds into, let's say, a unique factorization monoid? Of course, there are a lot of issues with the idea of such a generalization, but in principle, you could replace primes with the elements of a basis of the free commutative monoid, where I'm saying you to embed your monoid H. And second, I understand that you don't have any analog of the fixed divisor, which seems to be an essential part of your criterion, but maybe the fixed divisor is just a red herring. So my question for you is, suppose that H is a monoid embedding into a free abelian monoid, so that you can replace primes with the elements of a basis of this free abelian monoid. Then, can you imagine there is a chance to generalize your criterion to such a setting? Have you tried to do something like this?
Thank you, Salvo. Thank you. And thanks a lot for joining. We didn't think about it really. We didn't think about it, but I guess it could work. We didn't think about it. So an immediate generalization could be still, but that's still integer valued on subsets, but that's kind of a direct generalization. So that's kind of a direct generalization, but for monoids, we haven't thought about it because, yeah, we should come to the monoid experts also. Yeah, wow. So we've been mainly in this domain. Yeah, but we should think about it, Salvo, maybe at some point.
All right, thanks.
Okay.
Thank you.
And all the best.
Thank you.
Very much.
Hope to see you in July.
Hope so.
So I think we should stop here because there is another talk. Thank you very much, Professor Nakato, for being here with us. Thank you very, very much. Thank you.
Thank you. Thank you, Professor Rashida.
So now I'm looking for Professor Shileli. Professor Shileli?
Oui.
Are you ready? Vous êtes prêt, monsieur?
Okay. Yes.
So the next presentation is from Professor Shileli, that we would like to thank for being here with us in this event. His presentation is titled Cryptography and Non-Commutative Referential. So Professor Shileli, you have 30 minutes. The floor is yours.
Merci. Tout d'abord, je remercie le comité d'organisation pour cette conférence. Et j'ai 30 minutes et je vais se disposer de 15-20 minutes grâce à la prière de vendredi. Je m'excuse. Donc, est-ce que mon écran est clair?
On ne voit pas la présentation.
Oui, je vais partager.
Professeur Chileli.
Oui, professeur Chileli, veuillez partager votre écran en cliquant sur l'icône partager l'écran au milieu de votre écran. En bas, au milieu.
Professeur Chileli, est-ce que vous rencontrez un problème? Professeur Shamsuddin. I think that they are trying to resolve the problem. So we have to be patient. Okay. So Professor Shileli could not join us because of some technical problems. So we will stop here, I think. We'll close this session. So I will thank you. I want to thank you for your interest in this event. Hoping to see you next time face-to-face here in Morocco. So see you later in parallel sessions. Thank you very much. Professor Shamsuddin. So thank you for all the participants. Thank you very much.
Sorry, I have a question concerning the parallel sessions. I see that there are links for the parallel sessions are not determined on the website.
Okay. So Professor Shamsuddin.
Yes, as you said, Professor Rashida, we would like to thank all the participants for their interest, and we shall stop here. Unfortunately, Professor Shilali couldn't join us because of technical problems.
Professor Shamsuddin, just a minute. She asked you about the links of the parallel sessions.
Yes, we will put them in the few minutes. Already, we still have so much time before the. Yes, we still have more than 1 hour, so we will put the link in the rest of this time.
Okay,
yeah.
Thank you. Thank you.
Thank you very much.
Thank you very much.
And in the name of the organizing committee, we would like to thank all the participants in their interest, and also we express our gratitude to the invited speakers for their contributions. Thank you so much.
Yes.
And thank you very much, Rashida.
You're welcome. Thank you.
Good afternoon, Professor.
Good afternoon.
Does the parallel sessions start on its own time, which are given in the schedule?
Yes, we still have about 2 hours.
Okay,
they will
okay,
start
sir.
after 2 hours, inshallah. Yes.
Thank you very much, sir.
Thank you very much.
You're
Thank
welcome.
you. Okay, bye-bye.
Yeah, bye.
Thank you very much, Professor Rashida. Bye-bye. Bye-bye.